vectors would have. Okay, one of which is your directed line segment, another one is the column vector. Okay, so looking at practice now 1A, a directed line segment essentially is just a line with an arrow, okay, without the grid itself. But when it comes to a column vector, we use certain numbers to represent, okay, the direction and also the magnitude of this particular vector itself. So I ask you to go back to actually try out practice now 1A. So let's just check our answers. Okay. So for the line segment AB, or rather vector AB, okay, what we see as our column vector is that it is x direction starting from A, because A is the starting point. Okay. Towards the left, we recognize that there are negative 2 units, because the way we count our units is that on the right is positive, on the left is negative. And then we move upwards, okay, vertically. So we can only move horizontally or else vertically. Okay, going upwards, we have moved 4 units. It is a positive 4 units. Hence, in this case, our column vector will be negative 2 and 4. Okay? Sorry, negative 3 and 4. Okay? So that's our column vector. Okay? And then we have also learned how to find a magnitude of a particular vector. So in this particular case, where we have the vector AB to be negative 3, 4, the magnitude will be found by taking square root of negative 3 squared plus 4 squared, which gives us 5 units. Okay. Other than familiarizing ourselves with notations such as AB, which tells us the start point and the end point, we will also have notations such as C, where we write it with a tilde sign at the bottom. Tilde is being, in case you want to capture the pronunciation, spelled as T-I-L-D-A. Okay. That's the formal name of it, rather than telling me the curly sign at the bottom. Okay. So we write C tilde, okay, as the vector representing this one, and the column vector that represents it will actually be starting from here, because it's going this direction. We have moved negative 2 units to the left, okay, and then downwards, so that will be negative 2. So the vector itself is negative 2, negative 2. Okay, and then we can also find out what is the magnitude. And in this case, that will be square root 8 units. Okay. And then yesterday we also covered horizontal and vertical vectors. So horizontal vectors, because there's no vertical movement, starting from this point to that point, there are 5 units across and in the right direction. So therefore, DE will actually be 5, 0. And our vector F, okay, going downwards with no x component, so that will be 0, negative 3. Okay. Yesterday, something that I didn't cover is about measuring the magnitude of horizontal and vertical vectors. Okay. For horizontal and vertical vectors, it is obvious, okay, when it comes to the length, the magnitude, because it will be exactly the number of units, okay, that we can count. Okay, we just have to remove the direction. Okay, so negative actually tells us the direction. So therefore, in this case, for the vertical vector, okay, the magnitude will be a positive 3 units. Okay, you need not actually go about doing calculation, but if you would want to do calculation, okay, the value does come out to be the same thing. Right, so that is what we did yesterday. Okay, today, so that's just a very quick recap, especially for our SYF higher students yesterday. What we're going to do next is to learn about equal vectors, negative vectors, and parallel vectors. Okay, erase this up. I want us to take out the green paper that I gave you yesterday. For those that went out yesterday, let me just pass you. You pass one to Matthew and also to Jasper. Anybody, oh you have it? Anybody else doesn't have it? Okay. I think Matthew can afford it. This is handwriting sometimes a bit big, right? Okay, now let's continue our big paper. This right, this was what we did yesterday. Okay, we will continue by talking about certain vector terminologies. Erase that. So let's just give a header here, vector terminologies. Okay, I want us to draw a diagram. Okay, from 0 to 10 vertically. And then horizontally from 0 to 18. We draw some vectors. Let me just zoom in.
so excited.
Okay, I'm drawing this to help us understand firstly what are equal vectors. Okay, equal vectors like what the word mentioned suggests. Okay, they have to be equal, right? And equal in what sense? They have to be equal in terms of its magnitude. Okay, as well as same direction. Okay, so equal vectors will have to be same magnitude and same direction. So from the diagram over here, okay, what we see as equal vectors will have to be A and B. Okay, so as an example, A and B in this case are the equal vectors. Okay. However, for vector C itself, while the length is clearly equal to B and A, that means the magnitude is actually equal, the direction is actually not equal. Therefore, C and A versus A and B are actually not considered equal vectors. Only A and B are considered equal vectors itself. So, implication about equal vectors is that if vectors A and B are equal, then it implies that the magnitude will have to be the same. Okay. However, if the magnitudes are the same, it doesn't imply that the vectors will have to be equal. Okay. That means to say that, for example, we see that C, B, and A, they are definitely equal in magnitude, but we know very well that C is not equal to B, neither is C equal to A. Okay? So having same magnitude doesn't mean that we have equal vectors, but having equal vectors will mean that it is same magnitude. Okay? Then, next thing about negative vectors. Okay, negative vectors are vectors that have same magnitude, okay, but opposite direction. So in this case, as an example, A and C are considered negative vectors to each other. Okay, when I can write that A is equals to negative of C. Okay, and because A and B are the same, so obviously I can also write B equals to negative of C. Okay, because C is actually of the opposite direction from A and B. Right? The converse holds true as well, meaning to say that I can also say C equals to negative of A or C equals to negative of B. Okay. I want us to take a very important note, which is that opposite direction doesn't have the same meaning, okay, as different direction. Right? This one we have to be very clear, because even in real life, okay, if let's say I'm telling you that, for example, Xing Xuan is going to the left and she exits out of the door, but I'm going to the right. Okay, we are traveling in opposite directions. Opposite directions, no doubt they are different. But then not all different directions mean that they are opposite. Okay? For example, maybe Xing Xuan turns to the left, okay, but I just go backwards, okay, back to my table over here. Then we are clearly going different directions, they are not opposite at all. Alright? So we need to be very clear that opposite and different, okay, they imply different things. Right? So when it comes to negative vectors, they go in opposite direction. Okay? That we have to be very precise. the next one, okay, that is important is about parallel vectors. And for parallel vectors, they have the same or different direction. Same or different magnitude. Okay. They can also have same or opposite directions. So when it comes to parallel vectors, the magnitude really doesn't matter at all. So long as you are able to recognize that they are parallel lines, okay, they are parallel line segments, they are considered parallel vectors already. So as an example, okay, to this diagram, with reference to this diagram, we can tell that A, B, C, and E, they are actually all considered parallel vectors. Okay, D is clearly not parallel to any of them at all. Okay, we save a little bit of space over here so that we can add on later on as we learn more along the way. Any questions? So these three crucial terms we need to be very clear about: equal vectors, negative vectors, as well as parallel vectors. Okay, especially when it comes to parallel vectors, okay, there are some implications that will be useful later on. When you're done, I'd like you to turn to your next book, page 6. Turning back to my screen on my laptop.
Running out of sugar.
I want us to take a look at practice style 1B to learn also how to draw vectors when given column vectors. So in this case, we are given the grid. So use the grid that's in your work example 1. Okay, in part A, we want to draw the vector 4, -6. When given column vectors like that, it really doesn't matter where you start. Okay, it just matters whether the vector itself fulfills this column vector or not. So you can choose any point to start just to make sure, and you have to make sure you got enough space. Okay, so for example, in this case, with 4, -6, if let's say I'm going to start here, slowly. Okay, with 4, -6 over here, starting from here, okay, 4 would mean that we're going rightwards, okay, for 4 units, and then downwards for -6. So clearly I don't have enough space and I will need to adjust that. Okay, so maybe I'll adjust it to here. So 4 units to the right and -6 units downwards. That will mean that, okay, I will have a vector using a ruler to draw the straight line. Okay, a vector that looks like that, and it must be going in this direction. So this vector will be 4, -6. Okay? Alright. I want you to try, okay, part B, C, and D very quickly, okay, onto that grid that you see in work example 1. Okay? Give you about 2 minutes to work on that.
thought it was sounds like simple. Oh.
You're done drawing already, is it? Okay. Okay, so for negative 2, 3, okay, we're going to the left and then upwards. So maybe we'll start over here. Okay, leftwards negative 2 and then upwards 3 units. So this likely how your negative 2, 3 looks like. Okay, and then after that we have 4.5 and 0. So that means that going on the right, okay, 4.5 units. In this case, 1 square is 1 unit. So we will have to cover up to half a square. Okay, so from here to here, that will be your 4.50. Okay, and then finally, when it comes to your negative of 0, 1, that means that we're looking at 0, negative 1 as a vector. Okay, so 0 will mean that we're not going left and right at all. So starting from any point, negative 1 going downwards, it will be a vertical vector. Okay, so your vector looks like this. Okay. Now looking at practice now 2, as I mentioned earlier on about how equal vectors behave. Okay, so in this case, if you're given that A is equals to this and B equals to this, okay, since they are equal vectors, they behave just like our matrices. So we can say that these two vectors are equal. So the x component will be equals to each other. Likewise, the y component will be equals to each other as well. Okay, so solving these two equations will help us to find out the value of x and y. Okay, so we get that x is equals to 4 and y equals to 4.5. Okay, so that's how we solve part A. Then we want to write down the negative of A as a column vector. So since we have already found out the value of x and y, your A itself will be 4 plus 2 and 4 minus 4.5, which simplifies to 6 and negative half. So the negative of A would be 6 and negative 6.5. Then in part C, okay, we want to show that the magnitudes are actually equal. So the magnitude of A, upon a quick calculation, we will get square root, 36.5. Okay, and clearly because our vector B will also be 6 and negative half, okay, our magnitude of B will also fulfill the same calculations. Okay, and therefore the two magnitudes are equal. Okay. Unlike how we solve part I, okay, part 2 says that the magnitudes of A and B are actually equal. So that means that we cannot just simply say that the two vectors here are actually equal. We need to look at this magnitude itself. So in this case, that will be x plus 2 squared plus 4 minus y squared, followed by a square root. That is the magnitude of A. And then the magnitude of B, okay, the magnitude of B will be found this way. Right, then we proceed to solve. So we can square both sides in order to get rid of the square root. And we have no choice but to expand. Okay. Upon expansion, you see that your x squared will be cancelled on both sides by subtracting x squared. Okay. Likewise, our y squared could also be cancelled out because you can subtract away y squared on both sides. Okay. Then we can simplify to get 4x minus 8y plus 20 equals to 125 minus 20x minus 10y. The question wants y in terms of x, so let's place y on one side of the equation. Hence our y will be 105 minus 24x over 2. And then, as mentioned earlier, about how is it that when two vectors have the same magnitude, they may not actually have the same direction. Okay, so we will use that to explain for part B why A might not be equals to B. As a counter example, we could consider a case whereby A is following what we got in part I, that is 6 and negative half. And B, let's say it is negative 6 and half instead. Okay, so it is clear that the magnitudes will be the same, but the directions differ. A and B are not equal. diagram, okay, a figure that shows the positions of the point P as well as a vector AB, which is 4, 1. Okay, part I wants us to express PB as a column vector. So PB will be this way, and the direction following the naming itself will have to be from P going towards B. Okay, and therefore knowing the direction already, I can then form my column vector. And in this case, we are going rightwards for 3 units and downwards for 2 units. So rightwards will be positive 3, downwards will be negative 2. So the column vector will be 3, negative 2. Okay, I want us to pay closer attention to part 2 and part 3. Part 2 says that we want to plot the point Q such that ABQP is going to be a parallelogram. Okay, so with a notation like this ABQP, we must know that it is going either in the clockwise direction or anti-clockwise direction. So that is the convention whenever it comes to naming of a quadrilateral. So because we already have A, B, we are missing a letter Q or a vertex Q, and then going to P itself. Okay, so since P is over here, and since we have to go in a certain direction, in this case, we know that it's going to be anti-clockwise. In fact, usually it will be anti-clockwise. Okay, so A, B, Q will have to be somewhere around here. Okay, then going to P. So drawing my parallelogram, okay, I will need to have parallel lines. And in this case, okay, AB must be parallel to QP. So we follow, okay, how many units is actually going to the right and to the top. So 4 units right, 1 unit up. So from P, 4 units right, 1 unit up. So your Q will have to be over here in order to form a parallelogram that looks like this. Okay, so BQ itself as a vector will be this line segment here and in this direction. So rightwards 1 unit and upwards 3 units. Therefore, your column vector BQ will be 1, 3. Okay. Then by the same logic, when it comes to part 3, where we have A, B, P, R, okay, make a parallelogram. So we have to go in an anti-clockwise manner in this case. That means your R must be around here. So that means AB followed by P. That is half the parallelogram complete already. I must have another line segment that is parallel to AB. So that means from P itself, going down 1 unit and going to the left by 4 units, I will observe that my R has to be over here. So we get a parallelogram that looks like this shaded one. Okay. Therefore, for part 3, our PR, okay, will be this direction. So going down by 1 unit and then going left by 4 units. So negative 4, negative 1. Okay, yeah. Then in part 4, it asks, do the two vectors PQ and PR have the same magnitude? So because, okay, it is forming out of a parallelogram, surely their magnitudes will have to be the same. Because in a parallelogram, we have 2 pairs of parallel lines. Okay, so this and this, maybe having the same magnitude, okay, that means that your magnitude-wise will be equal, but then the vectors, clearly they are not equal because PQ is going in this direction, whereas PR is the opposite direction. Okay, so they cannot be equal vectors since the direction is different.
How they see it.
you are already familiar with what's going on in vectors, okay, usually I do not do subtraction of vectors. Okay, why? Because subtraction is just a very unique case of addition. Okay, so one very important concept, okay, that we need to know is that how negative vectors actually work. So earlier on, okay, we mentioned about negative vectors being like that. Okay, so what this means in vector form is that, okay, AB is actually equals to the negative of BA. Okay, so I can change direction by applying a negative sign. Right? So that means that if let's say AB is going in this direction, okay, then after that applying negative sign will change the direction. Okay, to this. Alright? So that's why I will rely more on the addition of vectors rather than subtraction of vectors. Okay? Now, first thing when it comes to addition of vectors, it's either you write this inside your notebook or you can write it on the reverse of that green paper that I gave you, whichever that you prefer. Okay. So one important thing is that when it comes to addition, let's say if I have a vector PQ and a vector QR, we have to always ensure that the middle two points, okay, Q have to be the same. In order for us to conclude that the addition of these two vectors gives us PR. Okay? So that is notation wise. Right? Somewhat similar to how we understood our matrices, where we needed the middle part to be equal. Okay? Or when it comes to matrix multiplication. In diagram wise, how this actually looks like is that if let's say I have a vector PQ going like that, okay, I have to add another vector QR. That means my starting point is Q, going to R, okay, maybe R is ending over here, so Q to R will be in this direction. Okay, the resultant itself, what comes out is that I'm walking from this path to here to here. It is as good as walking from this part P all the way R itself. Okay, so that is your resultant vector. So this another name for it is resultant vector. Okay, so it is really similar to what you would have learned in your physics, okay, when you draw your free body diagrams. You still draw free body diagrams, right? Okay, so the same concept, okay, when it comes to that, right? I usually always do triangles, okay? I don't rely on the parallelogram form, okay? Because we can always shift things around. So diagram wise, P to Q to R and then P to R, okay? Okay, so if let's say I have a grid over here, okay, I think maybe your grid space may not be enough. Okay, I have, do you want more grid paper? Okay, I just leave it over here. If you need one, you just come and take yourself, okay? Right? So, I'm just trying to be tidy, that's why I'm using this grid over here. So if let's say, okay, if I have PQ to actually be 6, 9, so for example, if my P were to start over here, okay, having 6, 9 as my PQ, okay, that means 6 units and 9 units upwards, so we will end over here. my QR were to be a vector that is 2, -3, that would mean that from Q itself, 2 units to the right and then -3 downwards. So R will have to be here and this will be my QR. Okay, the resultant vector in this case will be PR in this direction. Okay, for resultant vectors, we always use double arrows. And in this case, our resultant vector, just by looking at the vector itself, okay, we go from the left, go to the right and then upwards. So that will actually be 8 units to the right, and then upwards will be another 6 units. So we see that our vector PR is 8, 6 as a column vector. Okay, this fulfills our addition itself, whereby if I were to consider PQ plus QR, just by adding the 2 column vectors itself, matching the component to component, so 6 plus 2 will give us 8, 9 plus -3 will give us a 6. Okay, and it indeed gives us our 8, 6 vector. So diagram wise, okay, we visually see it in this manner. Okay, and addition of column vectors wise, we get 8, 6. Okay. Then let's take a look at whether the addition actually is consistent when it comes to the magnitude or not. So the magnitude of PQ, okay, will be 6 squared plus 9 squared followed by square root. That gives us square root of 117. And then the magnitude of QR will be 2 squared plus -3 squared. And that is square root of 13. Now when I look at the magnitude of PR, okay, we get a magnitude of 10 units. And from this over here, we can conclude that when I find the magnitude of the addition of the 2 vectors, it is not the same as adding up the 2 magnitudes separately. Okay, so this PQ plus QR is actually your PR. Vectors notation. We already saw that if given PQ plus QR as vectors, it simplifies to be the vector PR. Okay, and then what if instead we are given SR plus PS? Okay, and I want to simplify this notation itself. we need to know that for vector, it behaves somewhat similar to your algebra. Okay, it is okay to actually swap them around. So it is the same as PS plus SR, which then simplifies to give us PR. Okay, and if we were to have a longer expression, like PR to RS and SQ, we know that PR plus RS will give us PS, okay, followed by SQ, and S are actually the same, and therefore the notation simplifies to PQ.
Could you?
Right? So next we look at subtraction of vectors. Okay, I want us to take a look at subtraction by looking at practice now 8. Okay, so in practice now 8, right, we're told that find a vector represented by the double arrow in each of the diagrams below. So the double arrow vector for part I refers to this vector over here. Okay, for this particular vector, we know that the start point is here and the end point is here. Okay, you think about vectors like as though you're creating another pathway, another way of walking from start to end. So instead of me walking to the table directly in a straight manner, maybe I walk over to Zane, then I walk over to Ashley, then after I come over here. That's an alternative pathway that can reach the same destination. Okay, so from the start and to the end, right, I know that I can take one path that goes in this line here, okay, then after that going in this direction back to our end. But I know that if I have the start over here and then after coming down to here, right, okay, it is of the opposite direction as A. Okay, and being opposite direction, knowing our negative vectors, it will mean that if I want to go in this direction, the vector here is a negative A. Okay, so we have our resultant vector in this case as negative A, followed by adding up to a B itself. So this negative A plus B will be the vector that represents the resultant. Okay, so usually we think about things in addition is much easier, okay, and less complicated than thinking about it in subtraction, which can be a different set of thinking. Okay, you can see from your textbook if you want to look into it. Okay, they have a different set of rules, right? But I find that addition is definitely much easier, so long as you recognize that going in opposite direction is the negative of that particular vector. Okay, so part I, this will be the answer. Then looking at part 2, okay, with this being our resultant vector, and this being the start, and this is the end, okay, the alternative path that we will take is from the start going this direction, followed by this direction. So if I'm trying to go against, okay, B itself, that will mean that my vector is negative B, followed by A, okay, whereby the direction remains the same. Therefore, in part 2, my resultant vector will be negative B plus A. Right? Just like how we do usual addition, okay, there's nothing wrong if I were to switch it to write it as B minus A for this. And likewise for this, I can write it as A minus B. Okay. here.
It's not
Okay, from the start, following this pathway going down, okay, that will be a negative n, followed by going up, that will be a m cell. So the resultant vector will be negative n plus m cell. Okay, same thing applies for your part 4 and part 5. Okay, for part 4, in fact, it's already very nicely given to you, the start being here, following the path, same direction, following the path, same direction. So it is just your V plus W. Okay. And then for part, this part 4 and then part 5. Come in. From the start itself, we will go in the opposite direction. And then after that, for V, again we're going the opposite direction. So that will give us negative W minus away V. Okay. It is possible to so-called factorize out the negative as well. It means the same thing as negative bracket W plus V. Okay, because after all, if you compare your part 5 and your part 4 diagram, okay, the resultant vector of this and the resultant vector of this, they are actually going opposite direction. Okay, while your W and V are the same. So therefore, it makes sense that we have negative W plus V, which is the opposite of V plus W. So thinking about things in addition will be easier. So from one path to the next path, just add on, okay, to arrive at the end point itself. Okay, let's look at practice now 9, shall we? Okay, so practice now 9, we're given a parallelogram. That will mean that, okay, if you're given the vector OQ, which we actually label it as a small q over here, this is actually the same as the vector PR, which is also Q over here. Likewise, OP being defined to be going in this direction with a small letter vector P, it is the same as your QR in this manner. Okay, so that's what we can conclude from the fact that it is a parallelogram. Okay, then in PR for part I, okay, so as mentioned already, because they are parallel, PR start to end is in the same direction as O to Q. So PR is equals to Q. Okay, then after that for part 2, to find out what is RQ, RQ will be in this direction, which is the reverse or the opposite of QR. So RQ will be negative of P. Okay. Then OR being in this direction, okay, will be from O going to R. So there are a few pathways that we can take. One path will be starting from O, going along the direction of P, followed by going along the direction of PR. Okay, so we are going one direction and adding on to the next direction. So therefore, your OR is equals to P plus Q. Okay, because that is equals to OP plus PR. Okay, so just different kind of notation. So we earlier said also that in this notation, P and P, they are the same. The resultant will be OR. So that's how we get OR. then looking at part 4, to find out what is RO. RO will be in this direction, starting from R to O. So path that we can take is starting from R, I can go in this direction. Okay, then after that going up in this direction. So you notice that it's in reverse. So in this direction, the vector will be negative Q, and going up, it will be negative P. So our vector for RO will actually be negative Q plus negative P, which simplifies to negative Q minus P. For PQ, from P to Q, it is in this direction. Okay. One pathway that we can take is maybe you can go upwards. Okay. You can go in this negative direction, so negative P followed by Q itself, and therefore PQ will be negative P plus Q. Right, and then finally, looking at QP, okay, QP is in this direction, so I can do this path followed by this path, so it is a negative Q followed by plus P. About things like you imagine yourself standing there and then you walk a different pathway. Okay, and then think about it in addition, right, rather than thinking about it in subtraction. Right? When you try to think about it in subtraction, I always find that it is difficult and can be very messy as well. Okay, so that's why I practice doing more of addition rather than thinking of things in subtraction. Okay. So with that, and then we look at this question. I think this is your practice now 10. Okay, this comes of simplifying your notations. Okay, so for part A, we already know AB plus BC will give us our AC. Okay. However, when it comes to, like, say, part B, okay, then how do we actually deal with AB minus AC? Okay, like I mentioned, I always think about things in addition. Okay, so when we see negative AC, I want you to see it as though it is AB plus, okay, negative AC. And with negative AC, the implication of negative is that it changes direction. So negative AC is the same thing as CA, and therefore we can have CA plus AB. Due to the nature of addition, I can shift the terms around. Okay, and then it fulfills, okay, the requirement when it comes to addition, so we get CB as our resultant vector. Okay. part is the same, but it is a minus sign, so you cannot apply the same concept as our addition. We have to do the flipping, okay, of direction, like what I mentioned. So minus BC is the same as plus CB, okay, upon flipping of the direction, because the minus sign will cause BC to flip to CB, and then this will become a plus, okay. And then with AB plus CB, right, even if I change things around by rearranging the terms, I'm still going to get CB plus AB. Our middle terms, okay, our middle points will not actually be the same. So like in this case, our middle points are the same in order for us to add. Likewise, our middle points over here are the same for us to add. So in this case, right, with CB plus AB, it cannot be simplified further. Okay, which also means that we are not able to get a resultant vector. Then we look at PQ minus PR. So with the minus sign, I flip, okay, the direction of PR to RP. I notice that both has a P, so let's attempt in shifting them around, okay, by rearranging them into RP plus PQ. And we see that the middle is the same, and therefore it simplifies to a vector RQ. Okay, and then for part E, same thing again, switch them, become plus QR, and then it already fits in nicely whereby the middle tone Q is the same, so that gives us PR as our resultant vector. So even if you're given three different terms, okay, or three different vectors to add or subtract, okay, we do things part by part. So PQ plus RP, I can, okay, let me write it here instead. Switch them around to write it as RP plus PQ, okay, followed by minus RS. And RP plus PQ will be the same as RQ, okay, then minus away RS. Okay, and then minus RS is the same as flipping ARS to SR, and then we find that R is in common. So I'll rearrange them to see if it fits such that the center is the same, and that gives us SQ. Okay. Okay, so I'm really going through 5.1 all the way to 5.6 okay, very quickly because they are all the really fundamentals that we need to equip ourselves with okay, before we go into 5.7. Okay, because 5.7 is really the main theme of the entire chapter itself. Okay, so for tomorrow for home-based learning, I'm going to give the instructions on Google Classroom, so do look at it. Okay, I'll try
Bro
to
is
see
ascending.
if I can have a video, okay, regarding your remaining parts 5.4 to 5.6. Okay. So that will be your assignment. Then after that, when we come back on Friday, okay, we can go into the main gist of things.